Hello, good afternoon, everyone. Before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, we would like to introduce yourself, your name, your designation, company, and the country you are based in. It's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. Great. And thanks for confirming. I would like to thank you all for registering and taking time out on a Sunday to learn about the use of conventional and advanced NDT techniques in asset condition assessment process. My name is Aisha Khalik and I will be your introductory speaker for today. It's a pleasure to host this webinar for you. This is our 82nd webinar in the series of technical webinars that we are conducting. As a practice, we are conducting one webinar every month. Please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates. Today, we have an experienced panel of speakers. I am with my colleague, Mr. Ijazul Kareem Rao, who is the Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatun, she is the Director, Engineering Services, and Mr. Adnan Saeed, who is NDT Manager at Veloci, Karachi, Pakistan office. Moving forward during this webinar, we encourage you to keep asking questions to clear any doubts. We would definitely like your engagement on this topic. You can type your queries in the question and answer window and you will receive a reply in the question and answer window, or we will answer your question live. We will try to answer questions as much as possible during this session, as we will have a detailed question and answer session after the completion of the topic. Please accept our apologies if your question is left unaddressed due to the high volume of questions we usually receive. So we have to be selective. Furthermore, we will also be issuing participation certificates to all those who have attended at least 80% of the webinars and have participated in the discussions through question and answers. Since this is quite a technical subject, we will touch only key theoretical and practical aspects of use of conventional and advanced NDT techniques in asset condition assessment processes. We will be covering ASNT and ASTM NDT standards, ASME BP VC standards, ASME BP VC Section V overview, introduction of non-destructive testing NDT, importance of NDT in asset management, conventional NDT techniques, advanced NDT techniques, and others. During this process, we request you to follow us along with and keep asking questions to help us make this session as engaging as possible. Coming towards the safety moment, before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those who are around us. And now I will request Mr. Adnan to start with the topic.
Thank you, Ms. Aisha, for such an energetic introduction. Hello, everybody. Good afternoon. This is the time here in Karachi, and I wish every participant good time of the day, or whatever may be the case with you guys. I think you all can hear me loud and clear. Ms. Aisha, can you confirm you can hear me?
Okay. Yes, Mr. Saeed, we can hear you.
Okay, thank you. And I have a flood of messages in the chat box. Okay, so I will request my IT team if you can please hand over the control to me. Okay, so ASNT and ASTM standard. ASNT stands for American Society for Non-Destructive Testing. Usually, this is the most applicable standard and acceptable standard worldwide. There are many more, but usually in our industry or in Pakistan and in Middle East, majority of the clientele and industry accepts non-destructive testing standards from American Society. And ASTM stands for American Standard for Testing of Materials. So they are interrelated, as we will explore when we will go through the slideshow. Okay, now it's working. So there are some standards from ASNT which do cover trainings of personnel who are interested in getting their careers into non-destructive testing. So most of us are familiar with the ASNT TC1A. So this is the standard qualification criterion. This standard provides with the standard qualification criterion for the people who are interested in getting themselves trained in the non-destructive testing. Multiple levels you might have heard already, level 1, level 2, level 3, So these are covered already in this standard. SNTCP 189, it outlines the qualification and certification criterions. SNTCP 105, this provides with the topical outlines to be covered whenever a training session is dispensed to any non-destructive testing trainee. And the qualification and certification standard is covered by CP 106. And inline inspection personnel are qualified as per ILIPQ 2010. So these are some of the standards from American National Standard Institute and American Society for Non-Destructive Testing. Basically, they cover some topical outlines and criterions which govern the training and certification of the people who are going into the industry performing the testing on different and various techniques. These are some of ASTM's non-destructive testing standards. These are specific to the techniques. For example, E1444 covers specifics of magnetic particle testing. E165 covers for liquid penetrant testing. There are various multiple standards and they differ with the form of the material and the manufacturing process of the material. So this is a general guideline whenever we used to write procedures and specifications and instructions for our NDT guys, we usually refer these standards as and when required. ASME boiler and pressure vessel standards. ASME, as I have already told you, stands for the American Society for Mechanical Engineers, and BPVC, Boiler and Pressure Vessel Code. ASME was founded in 1880. First performance test code was issued in 1884. And it was the first standard we were published was in 1915. Latest edition, which is in working nowadays, is 2021. I hope in October or August this year we will have a fresh one. As it is told in the next tab, that edition is revised every 2 years. And some of the ASME standards are ASME Section 1, Section 2, which has 4 parts, A, B, C, D. Section 3, which deals with the nuclear codes. ASME Section 4, which is heated boilers. Section 5, which is a specific topic of our day session today. This specifically deals with non-destructive testing and conventional advanced NDT methods, their applications, limitations, procedures, and guidelines. There are multiple other non-destructive testing standards like Section 6, which guides us how to care and operate heated boilers. Section 7, power boilers. Section 8 division, which has 3 divisions, 1, 2, and 3. These deals with these specifically deal with the pressure vessels. Section 9, this specifically deals with the welding processes, welding, brazing, and fusing processes. Section 10, fiber reinforced plastic pressure vessels. Section 11, in-service inspection of nuclear power composites. And Section 12, transportation tanks, and B31.3 is for the process piping, and B31.1 is for the power piping. There is the 11 or 12 different standards involved in the B31 series. They all cover different aspects of the piping system. There is a general overview for Section 5. We will go through this. Section 5 specifically deals with the routines and what would you say, regimes of different non-destructive testing methods. Non-destructive testing, as you might be aware, or I'll try to enlighten you up, deals with some physical phenomenon which we try to use to our advantage without destroying the test object's future usability. So whenever that method, non-destructive testing method, which are various in their application and definition and types, are used in the industry, they are governed by ASME Section 5, as we will go in detail later in the session. some of the well-known non-destructive testing methods which you might have heard already about in the industry are acoustic emission, adapted total focusing method, ATFM, which is a sub part of PAUT nowadays, or you can say this is an associate technique, which is very advanced and very latest. AUT is automated ultrasonic examination. ECA is eddy current array. This is comparatively new also. EMOT, encoded manual ultrasonic examination. This is uh, normally routinely done every part of the world. Uh, Electromagnetic eddy current testing. This has various further branches also. Leak testing, like you guys must have seen vacuum box testing or hydro testing. These are both part of leak testing. MT is magnetic particle, NDE is non-destructive examination, PT is penetrant testing, RFT is remote field testing, RT stands for radiographic testing, ultrasonic testing is denoted by UT, and visual testing is denoted by VT. Acoustic emission, the class of phenomena whereby the stress already applied to any acid, like there would be a tank or pressure vessel or LPG bullet or LPG sphere. When an acid is under operation or under service, there are certain stresses involved, and those stresses, when they transit they generate ultrasonic waves or audible ultrasonic, which are made turned into audible ultrasounds by using different equipment. With this whole phenomenon, when it's applied into the industry for detecting those emissions which are generated by any acid under stress, is called acoustic emission testing. The area of interest of this specific technique is to evaluate overall health of the structure. If there are any stress displacement, stress transits into the acid, this means there is something wrong with that acid in terms of corrosions or development of any defects into the acid. Defect which could be detected by these are some definitions. Defect is a what would you say, abnormality or imperfection which is beyond acceptable limits. This is how we would be simply putting a definition of the defect. Whichever the specification is being applied, if any discontinuity or imperfection is beyond its acceptable limits, it would be classified as a defect. A discontinuity, remember, every defect has to be a discontinuity first, and then it is classified as acceptable or rejectable. When it is classified as rejectable, it becomes a defect, and if it is classified as acceptable, it remains a discontinuity. So every defect has to be a discontinuity first. You cannot directly transit to a defect without having a discontinuity. Eddy current testing is a non-destructive testing test method which uses uh, current induction principle, which we will explore later in the presentation. False indication, which could be a result of behavior of any object, test object, or its properties or its characteristics with the medium of the test, which is being used to uh, identify some of the properties. This interaction generates some indications which are not actually coming from a discontinuity, but are rather from the geometry or properties of the material. So these indications, when are evaluated, are classified as false indications. IQI sensitivity in radiographic image quality indicator are used to identify quality of the image being generated by any radiograph. Magnetic particle testing is the use of magnetic properties of a material to detect any discontinuity defect into it. Time of flight, if time of flight deflection is a testing method in which we use ultrasonic high frequency ultrasonic waves, and the time it takes to transmit from one end of the object to the other and come back is total time of flight. Ultrasonic is a form of mechanical vibrations which we use in higher frequencies to test objects. Visual examination is to see an object to evaluate its condition. It's a visual examination. So I hope you guys are alongside with me until now. We are trying to dive deep into the subject from here on with an introduction. Uh, Definition of non-destructive testing. As I have earlier touched the subject a bit, uh, when we test a material or a component uh, to ascertain its future usefulness and to ascertain and to assess uh, its properties without destroying the object itself or the test object, and also without disturbing its future usefulness. Any method of testing which fulfills these 3 or 4, 5 different criteriums already laid out has to be classified as non-destructive testing method. When is NDT needed? To my humble opinion, NDT is needed in the entire life cycle of any given asset. You see, from the raw material stage in the mining industry, we need to assess the quality of the ore or the raw material, as this will govern the quality of the end product. So we use non-destructive testing methods to ascertain the quality of the ore or the quality of the raw material. Then that ore goes into the primary processing, or as I can relate it would be a primary steel making process. Into the process, we apply non-destructive testing methods to ascertain the quality of the primary product, which would be raw steel, ingot forms, slab forms. Then those primary products would go into the secondary processing industry, rolling, forging, casting industries. There, the non-destructive testing again comes into the play to ascertain the quality of the product and to ascertain that no flawed product passes the assembly line or manufacturing line. So when those products are formed into secondary products are formed into the final product, into the plate shapes, into the girders, into the slab shapes, into various other forms, then those forms of the material are used into our industry, into the oil and gas industry, to manufacture tanks, pressure vessels, piping, and other valve assemblies, etc. And also the structure of the plant, which serves the purpose to hold everything together. So, to my humble opinion, the non-destructive testing methods, they play a very vital role in every step of the life cycle of any given product. So it begins its functionality or its usefulness from the raw material till the finished product, and then back again when the product serves its life and completes its life cycle. It is turned into scrap and sold over and reprocessed again, and the life cycle begins again. So there is involvement of non-destructive testing in every phase. Industrial application of non-destructive testing, as we have touched already, it's applicable into the mining industry for ascertaining the quality of the ores and raw materials, oil and gas industry, which we use to test and uh, ascertain the health of oil and gas assets like pressure vessels and tanks and piping, etc. Into the energy sector, already those assets are already also involved in energy sector, power generation sector, aerospace industry, heavy engineering complexes, and automobile industry. Importance of entity in asset management. So the importance of assets and knowing the asset management in non-destructive, how the non-destructive testing plays its important role in managing the asset life cycle. Uh, when we operate oil and gas plants, we know there are multiple assets involved, and during the process, we tend to get aging of the assets and also the service-induced defects. So if we will run our assets to the failure, it will have a very adverse effect on not only onto the operational efficiency but also on the life of your plant. So routinely, we go through extensive inspection regimes, which also involve non-destructive testing methods, different non-destructive testing methods as and when they may be applicable, to ascertain the health of that specific asset of that specific plant, and also to equip ourselves with the knowledge required to plan predictive maintenance and plant turnarounds and plant maintenance works, so that we could not be surprised by any unplanned shutdowns or any unplanned maintenance works causing loss of production or downtime. So there are multiple non-destructive testing methods already applicable into the industry, as we most of us already know. How do we make decision? How do we apply multiple non-destructive, as there are many available? So how do we decide which one is applicable in a certain situation and which one is more useful for us in a certain situation than the other? You see, there is a very famous quote that no NDT method sees all. This is why different methods are there. If any one non-destructive testing method, no matter how advanced it is, could have seen everything and could have provided answer to every question, there would not have been any need for developing such diverse non-destructive testing methods. So from the word go, we know that we must select the optimum non-destructive testing method for a given situation. Some of the key questions that we need to ask ourselves before deciding which method could be. These are not all. These are some of the questions. What is the expected location of the defect, or should I term it as what are we trying to find? What are we trying to look for? Nature of the defect. Nature of the material under observation. Obviously, the material under observation plays a very vital role in selecting the method. As you might, as an example, I would put two non-destructive testing methods in contrast: magnetic particle testing and dye penetrant testing. These are the two most widely used methods, and most of the industry people are aware with the inner workings of these two methods. So this would be an easy example to absorb. So we have a material and we want to apply a surface method or surface NDT method to it. How will we decide DPT is better or no, magnetic particle testing and would serve the purpose more so? If the material is ferromagnetic, uh, it would behave better and it would respond better to application of external magnetic source. And if it is not ferromagnetic, if it is from paramagnetic or non-magnetic families, it would not respond to the application of external magnetic force very well or not at all. So if it is for ferromagnetic, yes, MT would be the method to go with. But if it belongs to the families from paramagnetic or non-magnetic materials, MT would not serve the purpose. Then we will have to go with the dye penetrant testing methods. But the first question, expected location of the defect. If we already expect that defect has to be a subsurface or it has to be covered from the surface, then the question of DPT goes out of the box. Then we have we have to consider other non-destructive testing methods, which could be applicable to the paramagnetic material, but can also detect the defect which lies below the surface. So these are some of the key questions which we ask ourselves when we face a situation where we have to decide which method we need to apply to assess any given object. What are different advantages of non-destructive testing methods? As we have gone through already some of the key points, uh, uh, in majority of the testing conditions, we do not have to get the acid off stream. It remains on stream, and we can test it without any adverse effect to the results being produced. Uh, it can help you plan your shutdowns and reduce your shutdowns. How can it reduce your shutdowns? It can plan your maintenance work before you. You know beforehand, you know the condition of your assets beforehand, so you can plan your maintenance runs accordingly. So no surprises in terms of failure of any asset, in terms of leakages being observed unknowingly, unplanned, and shutting the plant down for maintenance work. So it can reduce the downtime of your assets, because now you can have plant maintenance, safety of the assets and the operators. If your assets start to fail without warning, or without you knowing prior, those are not only dangerous for the production, for the asset, but they are also dangerous for the operators which are operating in the near vicinity. So fitness for service assessments are helped with the data being gathered by non-destructive testing methods. Remaining live assessments could be performed because the data required to calculate those numbers are provided by non-destructive testing methods. Uh, some of the conditions which are inaccessible to otherwise assessment methods are also helped with the non-destructive testing techniques. Um and these are some of the advantages which we usually see in the industry for uh, non-destructive testing methods. Okay, I am, excuse me for a bit. I am seeing some flood of the question in my Q&A. Okay, okay. So I would like to let you guys know that or ask you guys to vote for which would be convenient for you. I have today planned with my colleagues that we would have a Q&A session at the end of this session, which is around 136 slides. And I'm trying to run as fast as I can without considering.
Adnan, if you want to have a Q&A session in between, you can have. No problem.
Yes, sir, I can. I know I can have it, but for the convenience of the day, if we can have an interactive session at the end of this slideshow, it would be more beneficial for the participants.
No, at that time, everything would be gone. At least now, whatever questions would be there, you would be able to answer.
Okay, there are some.
In the middle, no, like 50 slides gone, 136, let's say, after completion of 70 slides, you should have a question answer session. Ali and Adeline, please try to organize that at completion of 70,
Okay, sir.
75 slides.
So shall we proceed? Okay, guys, we can have a question answer session in between, and at the end of the session also. So there will be two Q&A sessions. Okay, I'll handle the Q&A. I'll handle the Q&A. No worries, no worries. We'll have a small break of 10 minutes, and I'll try to answer as many questions as I can. But you guys are, don't worry, you can send over your questions to our panelists, and we will try our best to answer them even if the session is over today. So no worries, your question would not be left unanswered. Okay, let me get through this. Limitations of non-destructive testing techniques. As I have already touched the subject, there is no non-destructive testing technique in the world as of today, I know, which could claim that it can provide answer for every situation. This is the first and foremost reason why there are so many non-destructive testing techniques available to select from, because every technique has its own set of applications and its own set of limitations. So when we sit on the chair and trying to make decisions about how and what we need to do with when it comes to non-destructive testing methods, the questions we ask ourselves, we have already gone through them. So those are the questions we ask ourselves because there are so many techniques available. So sometimes the questions we ask ourselves are more of economics uh, part than the technical part. So the economy of the testing is a very major factor also. If a condition is being provided and it could be tested very economically with a very simplistic of the approach and very conventional of the method, we usually do not go with it, and it is not absolutely necessary to go with advanced NDT techniques. Yes, there are advanced NDT techniques which provide with a higher degree of surety and higher degree of recordability and repeatability, but it's not absolutely necessary to go with the advanced NDT techniques because they are oftentimes more costlier than conventional NDT techniques. So these are some of the questions. These are some of the applications and limitations or different advanced NDT techniques. As we will go through most of them today. But no technique, no NDT technique, whether and conventional or advanced, can claim that it can answer all the questions posted to it. So most of the time, we need to combine few techniques together to answer some questions and to answer some other. The other technique will complement the other one technique. And most of the time, we combine 2 and 3 and 4 different advanced NDT techniques to answer all the questions being posed to us. So there are basically this is not you see this classification is not provided by any international standard, but as a norma, we usually divide non-destructive testing techniques in two classifications: conventional non-destructive testing techniques and advanced non-destructive testing techniques. I'll get back to the grounds on which these are classified, but first we need to go through what techniques are conventional, considered to be conventional, and what techniques are considered to be advanced. And this could vary with the industry and the organization grounds. So in conventional non-destructive testing techniques, there are some of the very most commonly known techniques such as DPT, MPI, RT, UT, VT, ET, UTG, and this sort of stuff. These are most commonly used. Most of the people are aware of them. Either they usually see them being done on routine basis, on daily basis, or they are part of part of the crew that gets these things done themselves. And in advanced NDT techniques, we have eddy current testing, and we have phase delay ultrasonic testing. We have real-time radiography. We have automated or semi-automated ultrasonic testings. We have CHIME, which is creeping head wave inspection method. We have LORUS. We have guided waves, or alternatively also known as LRUT in the industry. We have far field eddy current testing. We have near field eddy current testing. We have so many other non-destructive testing techniques which we will go through today. So the conventional part, the dye penetrant testing is the most simplest of the all. Actually, it is actually direct aid to visual inspection. Which visual inspection we are all aware. When we visually assess a condition of any test object, like wear, tear, misalignments, very large cracks, paint removals, blistering, These sort of findings we usually detect and evaluate based on the visual observations. But sometimes we need some help to enhance the visibility of any given situation or any given indication or any given discontinuity. We suspect it to be present there, but we are usually unable to resolve or visualize it very visibly. So we need a aid, we need a help from a testing technique which would enhance its visibility, which is the specific case for dye penetrant testing. It's just an aid to visual inspection. It just helps very small defects to be seen, or their visibility to be enhanced, to be seen easily. Uh, uh, it is very easy to execute, where no any special arrangements are required. You see, it is the most simplest of non-destructive testing techniques. So the training required for getting certified and getting acquainted with the non-destructive testing like DPT to be done is very less. Uh, Regulations are not that strict. It's easily doable. No special equipment is also required. It is very mobile, very uh, uh, portable test instrument. You can have 3 or 4 canes alongside, and you can take them anywhere you want. So, and it's also easily available. It's very cheap also to be done. So these are some of the advantages of non-destructive testing. There are also some limitations, which are this method cannot be applied to the porous material, as it would trap your penetrant and render anything present unseeable, unresolvable. Surface preparation required is at times, not always, at times it is very extensive. Uh, Consumables which are available are highly flammable. They are usually available in the form of an aerosol can. Uh, uh, and you also need to impart proper ventilation if you are doing this in the confined spaces, as the consumable, they are also rated as carcinogenic on their labels. So you have to get some safety precautions for yourself. You have to cover your breathing orifices, so that you do not inhale these consumables, and you also have to cover your hands and skin so that you do not come in direct contact with the consumables. Otherwise, it's very safe to operate. Dye penetrant testing is a very reliable detect for surface defects. Obviously, those defects which you or the discontinuities which you are trying to detect through application of dye penetrant testing or liquid penetrant testing, as alternatively known as. Uh, it depends uh, on the on the location of the defect where it is present. So the probability of detection for non any for liquid penetrant testing is directly dependent on the defect's openness to the test surface. If the defect is not open to the test surface, DPT might miss it because it needs an opening to penetrate, and the opening, if it is not there, DPT would remain of no use in that situation. So if the defect is open to the surface, and the test object is not porous, so that it may absorb the uh, penetrant material, your probability of detection or accuracy of detection for dye penetrant testing would be highest. And if your defect is not open to the test surface, the probability of detection for dye penetrant testing will remain at its lowest. So, as I have already told you, the accuracy or probability of detection for dye penetrant testing, it relies on the condition of the test object. And that condition specifically is where if the defect or the discontinuity is open to the test surface or not. If it is covered with any form of any form of layer such as paint or grease, dirt, it would not remain open to the surface and DPT might miss it. And on the other hand, if the test object is very porous or it reacts with the penetrant material or it absorbs the penetrant material, in that situation, you would also not be able to resolve any presence of any discontinuity from the background. So the probability of detection or the accuracy of testing will go down. In a nutshell, is if the test object or the condition of the surface of the test object is not up to the mark, the accuracy of the test in case of the dye penetrant testing or liquid penetrant testing would go down drastically. So you need to be very careful about the surface condition of any test object which is to be subjected to dye penetrant testing. Radiographic testing. Radiographic testing is most widely and most commonly used, and it's one of the oldest testing methods in the industry. Usually, it is used to detect cracks in trapped air into the which is called inclusions, foreign inclusions, thickness measurement, profile radiography. These are some of the key applications of radiographic testing, but let me tell you, this is not where it ends. These are some key applications. Radiographic testing uses some sophisticated tools, as we have seen in case of dye penetrant testing. The need for tools is not very much. So the need of tools, when it is removed from any testing or testing regime, it becomes less costlier. And the more the tools are involved, the more the cost goes up. So economy of any testing, it depends on the involvement of how many different tools and consumables are being utilized to get the result. So one of the key consideration when we make decision about any non-destructive testing method to be applied, as I have told you already, is the economy of the test. If it is too costly for getting the results, it would be of less utility. So RT uses radioactive sources. Radioactive source could be naturally occurring in the form of cobalt or iridium-192. There are different naturally occurring radioisotopes which are used in the industry. And also we have artificially generated X-rays, which we use X-ray tubes to get X-rays from. Then we need X-ray films which get exposed from the X-rays and generate an counter image or a mirror image of the object being tested. Then we need IQIs, which are image quality indicators. Then we need densitometers to ascertain if the density of a radiograph is achieved or not. Then we need film viewers to view those X-ray films for evaluation and interpretation. Advantages of RT are it gives permanent record in the form of radiographic film. It can test wide range of materials and it can detect wide range of defects also. It is suitable for majority of the metallic materials and also for some special ceramic materials. Some other plastic materials also subjected to non-destructive testing, which are classified to be polymers or plastics, but they are high density plastics. So they are also subjected to non radiographic testing for their suitability. There are also some limitations associated with non-radiographic testing, and the first and foremost is the ionizing radiation. It is very hazardous to any life form. So human life, which is operating the radiographic equipment, or IR-192 sources, gamma ray sources, or X-ray sources, they need to be protected from exposure to excessive radiation, and also other people who are not associated with the uh, radiation work, but are unaware that radiation work is being conducted in their near vicinity. They need to be protected from excessive exposure, unnecessary exposure to the ionizing radiation of RT. Very special arrangements are required. Obviously, these special arrangements are required not only to get the equipment to the test object, but also to protect the radiation worker and the other people which are not radiation worker themselves, but are also working in the near vicinity. These special arrangements are required to protect them from exposure or overexposure to the ionizing radiation. Maximum thickness limit is 60 millimeter of steel in majority of the cases. Not this is not a what would you say, a thumb rule. We can exceed this limit, but obviously to exceed some of the limitations, we need a special equipment to be involved, which adds to the economy of the test. Gamma rays cannot, or X-rays cannot penetrate into the very dense materials like lead. It is a very dense material, so gamma rays cannot penetrate it. This is true up to some extent. Some thickness ranges are uh, penetrable by X-rays or gamma rays into lead also. But if steel is being penetrated up to 60 millimeters, that would remain less than 10 millimeters for lead. As the density of any given material increases, the penetrability of the gamma rays or X-rays decreases, and it's directly proportional to each other. So it goes down, inversely proportional, sorry. It goes down as the density increases, the penetrability decreases. Two-dimensional defects, also called planar defects, cannot be observed in RT. They can be observed in RT, but they cannot be accurately measured. You see, we have a planar view of an X-ray. It is just a one-dimensional image. It can also only give you the length of uh, any given indication, and then you evaluate it as per the specification. Either it is discontinuity or a defect, it is acceptable or rejectable. But you cannot ascertain its height or its volume from a given radiograph, because a radiograph is only giving you a one-dimensional image, so you cannot measure its other dimensions. So whenever the specifications, some of the stricter specification nowadays require to measure at least two dimension or at least a volume of the defect to or the discontinued to come up to any judgment regarding its acceptance or rejection. But in case of radiography, you only get to see only single dimension, which in majority of the cases would be its length along its axis. The skill to execute the job required is very high, because you are not only exposing radiographic films with the radiation, but you are also required to protect yourself from excessive radiation exposure, to protect other people around you from the excessive radiation exposure, and also to control the exposure of radiographic film up to the mark that it conforms to the image quality indicators specification, without compromising the image density required by the specs also. So it is a tight walk. So to walk this tight walk, we need very skilled and very trained operators to handle these sensitive equipments and to carry these sensitive jobs, which is oftentimes not uh, uh, permissible in certain situations. So there are other test methods to be considered. Accuracy or probability of detection, as we have gone through the applications and limitations of the radiographic testing, uh, we have come up to some limitations which depend on the density of a given material to be tested. In terms of thickness, we have seen there are some limitations. In terms of application, we have seen there are some limitations. So whenever a set of limitation is introduced into the testing system, the probability of detection goes down. So in case of radiographic testing, generally 0.3 millimeter can be detected using conventional radiography in steel. But obviously it depends upon the wall thickness, it depends upon the density of the material, it depends upon the geometry of the materials also, it depends upon the content of of the object also, if it is filled or if it is empty. And if it is filled, if it what is it that it is filled with, what is the density of the medium also. The type of defect which you are trying, it is the primary question, as we have spoken already. The type of defect is all very important, or all important to know if it could be detected with radiography or not. So the primary question when we ask ourselves what method is to be applied is what are we trying to look for. And when we are going for radiographic testing, the primary question here also is what are we trying to look for. If we are looking for some shallow defects which are open to the surface uh, and are very fine, uh, and it's a very dense material and very thick material, naturally we would refrain from going to hit it with the radiographic source. We would rather go with any surface method if the testing objects material permits. And if the material restricts us with some certain entity testing methods, we can also switch to other methods for testing such objects, rather than exposing them unnecessarily to radiographic testing. So again, the very important thing to know, there is no single technique in the world which can answer every question. So you have to ask yourself, what are we trying to look for? What are we trying to find the answer for? So that question would bring up most of the answers itself. So again, the ferritic wells or a POD curve for radiographic testing, it goes down with the density of the test object, with the thickness of the test object, with the uh, radiation frequency of the radiation you have got, either it's X-ray or it's gamma ray, or and the radioactive source also, either it's IR-192 or it's cobalt. So there are so many different factors to consider before provide a judgment upon probability of detection on any given entity technique. In case of RT, it depends upon density of the material, it depends upon thickness of the material, it depends upon the material itself, it depends upon what are you trying to find out, it depends about on what the specs are required to what are the specs requiring you to achieve in the first place. Either you can achieve it successfully or not, either you are able to protect yourself from the excessive exposure to the ionizing radiation without compromising the quality of the test. So these are some of the factors which determine the POD for radiographic testing. These we have already touched. So in some of the international standards as IAW, and there are some codings as green, blue, brown, and black, which runs from R2 to R5. These are sensitivity levels for different situations. And the sensitivity curves you have, POD curves you have seen above, like A and B. And these are the explainers for those POD curves. These are different situations being posed to radiographic testing regime, and the probability of detection with the change of one single parameter. The change in the probability of detection is being explained here in this slideshow. You can refer it back again. to achieve a highest possible POD value, as you have already gone through the subject, you need to have a certain set of information predisposed to you before you get to the testing job. If the acceptance criteria is very strict, you will have a higher reporting level. Obviously, the more indications you record, the more you have to report, as the acceptance criteria requires it. Again, as I have told you already, it depends upon the specifications you need to follow. It depends upon the film quality required. Uh, as and the specs require you to maintain a certain degree of density without compromising the visibility of certain diameter of a wire in a given IQI. If those specifications are very strict, it becomes even difficulter. Type of radiation being used, and the object under test. So the amount of this slideshow tells you the amount of restrictions and limitations you add into the testing regime, testing system. Its POD will go down by each introduction of every limitation. So if you are adding limitations fold by fold, the POD is going down fold by fold. Now, our next testing technique is magnetic particle inspection, MPI or MT, as alternately known in the industry. It is 1 degree above dye-penetrant testing in terms of simplicity, and or you should term it below, because it involves some degree of equipment more than the DPT involves. So it gets a bit more complex and compounded. It requires a certain more degree of training to handle, because because of the involvement of some of the specialized equipment to be used. Uh, so uh, we induce magnetic flux into a ferromagnetic material. That ferromagnetic electromagnetic flux tries to flow through the material, and given the permeability of a given material is uniform within the material, if there is some resistance to that permeability or resistance to the flow of the magnetic flux, the flux lines would try to bend their path to choose the path of least resistance around that resistive boundary. And in this effort, they would create a leakage field onto the test object, which then in itself starts behaving like another magnet. So when we spray our magnetic particles onto the test object where there is a leakage field, those test particles, being ferromagnetic themselves, tend to accumulate just around that leaking magnetic field. So this is the region, and this is how we visually detect the accumulation of the magnetic particles, and this is how we evaluate presence of any surface or subsurface discontinuities or defects into a ferromagnetic material by using MT. Sometimes magnetic yokes are used. Temporary magnetic yokes are used, which are power operated or battery operated. Sometimes we use permanent magnetic yokes as per the need of the day. Some consumables are also involved into the testing regime, such as some contrast paints. The contrast can differ in its usually it is known as white contrast, but it can vary in its color depending upon the color of the or color background of the test object. If it is already enough contrasting background for black or red magnetic particles, we do not need to apply contrast paint at all. We have already a conducive background to operate with. But if the contrast is somewhat somewhat not conducive, or it's near the color of the particles themselves, we need to have a conducive background so that we can differentiate between the accumulation of black or red particles from the background, so that we can accurately size and mark the indication being present on the test surface. Power supplies is not absolutely necessary to have in most of the cases, and after having battery operated equipment nowadays being available very easily into the market, this need is has diminished already. But in some certain situations, the situation demands to have a power supply available to operate some of the specialized equipment on site. Advantages of the MPI are advantages for DPT. It is very easy to execute. The amount of training required is the amount of time you need to invest into getting trained for MT for a certain level. It's good amount of time, but it's not comparatively that much as required for other non-destructive testing methods such as radiographic testing or ultrasonic testing or leak testing stuff. Results are obtained in very short time. Actually, they are not that much of a time. They are real-time results. No special arrangements are required at site if you are operating with battery-operated equipment. If you are not, unfortunately, you need to have a power source. Equipment is light in weight. Yes, it's portable, and it can be carried at any location, anytime. So there are also some limitations associated with the magnetic particle testing, as there are application or advantages. Calibration of the instrument is sometimes required. Um, it can test only ferromagnetic materials, as you need to have a material which would respond conducively to external magnetic source. Operator needs to be skilled in not only operating the equipment but also to evaluating the findings you get from applying the ferromagnetic testing or MT. Surface preparation oftentimes is required, but it is not as strict as it would be for dye penetrant testing. You need to sometimes remove some of the layers if present, which could interfere with the induction of induced magnetism, which could interfere with the propagation of magnetic flux into the object. So you need to, if electroplated objects are there to be tested, you might need to remove the electroplating first. And we have already discussed, in certain situations you might also need to have a power supply on site. So the POD, again, I would say it's dependent upon the mix of advantages and limitations present on that actual work day, on the actual test object. If it is more prone to the limitations, then POD goes down. Then though there is no point in using a technique which has very limited POD for a given situation. And it is, if it is more prone to the advantageous situation, if number of limitations present on site or on the test object are very low, then the POD goes up drastically. So as with any other NDT technique, the POD for MPI is dependent upon the set of application and limitations being available, or the mix of the application advantages and limitation being available to you at the day, or at that with that object under testing. That would determine what actual POD is available to you to operate with. So the ability of detecting surface is dependent on two major variables: defect depth of the defect, as induced magnetism does not usually flow very deep into the test surface. It sticks to the surface it is being induced from. And defect length. The result regarding defect height, usually some specifications tell us that usually if a defect is present more than 2.5 millimeters deeper into the ferromagnetic material, you cannot detect it using MPI. If they are posing a very little resistance to the flow of magnetic flux, you might lose them. If the defect is oriented parallel to the direction of the flow of magnetic flux, you might miss it. So POD depends upon multiple parameters. It is not a simple number to give or put or write somewhere. It has to be calculated for each given situation on the day. As it is evident from the slides, tab number 1 depends upon various factors, surface conditions being one of them, and the objects, the material being part the requirement number 2. What are you trying to find out would be the requirement number 3, and how are you going about the testing regime on that day is requirement number 4. And the testing equipment you have, the particle size you have, the contrasting background you have got. These are all of the factors which weigh in on a POD of MPI on a given situation. So as an example, we have provided you with the one situation and calculated its POD. But for any given test situation, you have to go through and you have to calculate and estimate the POD for that specific test object on that specific day with your specific set of equipment you have got. So, gentlemen, we are through to 73 and almost halfway, including Miss Aisha's intro also. So I'll take the credit for coming to the halfway myself. If you guys have any questions up till now, you can post them. I'll try to answer them, or my colleagues will try to answer them. And from now, we will have a 10 or 15 minutes Q&A session, and then we will proceed with the remaining of the session for the day.
Firstly, from Mr. Afan Ahmed. Mr. Afan, can you please unmute yourself and ask your question, please? Mr. Afan? Okay, I will just read the question for him. What are the examples of industrial porous material related to the oil and gas industry in regards to use of DPT? Mr. Adnan, please answer the question.
Okay, Eldin, I'm very sorry. I am unable to resolve what the question was.
Hello.
You can hear me?
Mr. Afan, please answer your question.
Hello, can you hear me?
Yes,
Yeah, I
we
can hear you.
Yeah, Assalamu alaikum.
Wa alaikum assalam.
Actually, there are two questions I already posted. Now, one is, I think it's not yet discussed. The question related to DPT, it is already discussed, but I just wanted to know what are the examples of the porous materials in regards to DP in our oil and gas industry that are used. Yes, sir. My question is over. Second question is also there, but I think it will be discussed further if whether it will be there or no.
Okay. Let me answer.
ECT and IRIS. Actually, we are doing ECT and IRIS here. Our refinery. So I'll ask the question.
When we'll get to the DPT or ECT and IRIS, I'll answer that question. First, we'll answer your DPT question.
Okay, next question.
Can you hear me?
Yes, I can hear you.
Okay. Some of the examples of the porous materials are casted objects, casted products, wrought iron products. Some of the porous objects are available in the service industry. For example, when a pressure vessel or a piping system is put into caustic service, it tends to create a pitting corrosion. It also turns the material surface porous. The prime example, if you want to compare any test object surface with something, and tell yourself or come up with the answer that if the surface is porous or not, if you have observed a bread.
Yes.
Yeah, the surface of the bread itself, it is the prime example for being any object to be, or any test object or any material to be of porous surface. These are the conditions uh, which retain the penetrant material into those small pores. And when you process that surface, even then, though, that penetrant would not get out of those pores completely. And when you will apply your developer onto the surface, the entire surface of your test object would the entire surface of your test object would become reddish, and you would not be able to differentiate between any presence of any discontinuity or the red background, which is caused by the porous surface. I hope I have answered your question.
Yes, yes. Thank you very much.
Next question from Mr. Salim Khalid. Sir, please ask your question. Mr. Salim Khalid, you're already unmuted.
Okay, Mr. Salim Khalid. I hope I already know you. Mr. Salim Khalid is from one of our most esteemed clients, if I am correctly recognizing him. So coming back to the question, which if material is examined for surface defects. Okay, the primary question here is what are you trying to look for? So the answer to that question here is I'm trying to look for surface defects, and from surface defects I am assuming the defect is open to the test surface. So when the test surface is open to when the defect is open to the test surface, hands down DPT would be the best answer. But if your material is ferromagnetic, and you suspect that these open to the surface defects might also have some associated depth to them, and also would have some end of the tip hairline fractures associated to them, and some jagged geometry also. So I would complement penetrant testing with MT. Penetrant testing for screening for absolute detection of the area of interest, and then complementing it with one run of MT to ascertain that there are no associated jagged branch cracks or branch defects with that defect also present. I hope I have answered Salim Khalid Saab's question.
Hello.
Any other question, please?
Next question, sir, from Mr. Malik Shakil.
Okay, Mr. Malik Shakil.
Please ask your question, Mr. Malik Shakil.
Assalamualaikum.
Okay,
You can
Mr. Khalid.
hear my voice. Assalamualaikum.
Walaikum assalam. Who is this? I can hear you.
Okay, thank you. Sir, my question is this: during the RT,
Your good name, please.
my name is Malik Shakil.
Malik Shakil. This is your question also. You have typed it.
Yes, sir.
Malik Saab, I would excuse from answering this question. This is not relevant to our today's subject. If you need you need answer of this question, you can post to our panel of panelists, and
Yes, sir.
we will try to come up with the question.
Okay, sir. Okay.
Yeah. You may proceed with your next question if you have any.
Okay.
Affan Ahmad Mahmood Alam Khan. What are the examples of industrial porous materials? I have already answered this question, Affan. If you have missed, I'll try to repeat. Some of the prime examples for the industrial porous materials are the casted objects. The direct sand casted objects are some of the prime example of porous industrial materials. Some valve assemblies you might see, some wrought iron products you might see in the industry, and some obviously some surface damaged fine materials also sometimes behave like porous materials.
Okay, next sir, Mr. Ispania Lavde. Please unmute yourself and ask your question.
Okay. I'm sorry if I will not try to pronounce this name. I'm sure I will brutalize it. But I'll try to answer your question. What are the quality control in WBS? This is not relevant to our today's subject, Mr. Whatever your name is. But you can write this question to our panelists and we will try to answer this later. Okay, same guy with another question. Which RT is best suitable for pipeline welding of 12-inch dia, 11.2 mm wall thickness? The simple RT, the one you use routinely into the industry. It's double wall, single image, radiographic. Okay, one question from Mr. Salim Khalid we have missed above. If you can please scroll up. Yeah, Mr. Salim Khalid is asking. It's a very interesting question. Okay, Mr. Salim Khalid, you are asking according to my perspective, the economy matters more in the selection of the NDT method. Could a owner user may compromise on potential damage consequences due to high cost of NDT rather than the quality of object? So, when the question is posted, Salim Khalid Sahab, this is answer to your question. When the question is posted between the quality and the economy will not govern. The quality will always govern. And when we say it is an important factor also, we say this not on the cost of quality. If considering the economy is going to cost us quality, we will always put the quality first on the top shelf. But if the quality can be maintained with giving some cushion to the economy also, then that economy cushion would be considered only in that situation when the quality is not being compromised. When the quality is being compromised, economy rests on the back seat. So the next question is RFL Harsi. What is the preferred NDT method used to find localized discontinuity in piping baseline? Localized discontinuity. What type of localized discontinuity is that? If I'll assume I have to answer the question, I'll assume that it is the service induced pitting corrosion, which is the form of localized discontinuity in piping. It seriously depends on so many different factors. So in majority of the cases, what I will suggest to my client, being a student of non-destructive testing for 17 years, I'll suggest my client to go with the screening run with guided waves, or alternatively known as LRUT first, and identify the areas of concern, actually those areas which show some sign of presence of discontinuity. Up to some extent, the information also brings up some degree of the damage also. Then we can go with our other NDT methods to ascertain how much and up to what extent the actual damage is. So this would be the answer to your question. As I have already said, no single technique answers all the questions. You have to sometimes couple up 1, 2, or 3 different techniques to bring what you actually need to know. Imran Qasim Sheikh, what are the IQIs to be crossed when we have different material thickness? I'm not sure what you are trying to ask here. The specs you are doing radiographic testing against, they are the authority which would tell you what IQI is to be used. And if you are following any specification at all, I assume you or the technician which is performing the radiographic testing, he already has his approved NDT procedure in his hands. So if he has approved NDT procedure in his hands, the IQI to be used is already instructed to him in that specific procedure. So nobody in the field has to decide on his own what IQI is to be used. It is already provided by the specifications. What is the Jamshed Khan? What is the best NDE method for nozzle joints inspection? So,
Mr. Jamshed Khan, please unmute yourself and ask your question. Mr. Jamshed, okay, if he's still not here, Mr. Adnan, you can read the question and ask.
okay,
And
I have
answer.
read the question, Aldin. Thank you. The and best NDE method for nozzle joints. Actually, um, it would be PAUT to me, always hands down. But before suggesting you something, or before suggesting you with an inspection regime to be applied, I have a set of questions you would be required to answer. This is for me to come up with the specifics of what PAUT setup I need to effectively handle your inquiry. So the question here, I hope I have answered it, but it is not complete to come up with a practical solution. Next, please.
Okay, Mr. Ayman Sultan.
Mr.
have
Ayman and lots of
Yeah, sure.
apostrophe Sultan. Okay.
Yes.
So is
Ask your
it
question.
effective to prioritize entities, or there is an optimum combination to perform some tests before other tests for an overall better understanding of decision? Oh, okay. So the approach, this is a philosophical question to me. How would you approach your need? Uh, like as I have answered already a question that in a certain situation, uh, me being an NDT student for last 17 years, I would suggest my client to break his task into two different parts. First one would be to screen and to pinpoint or underline to the areas of actual concern. So once we know what the areas of concerns are, then we can approach with a direct method to ascertain the extent and degree of damage that has been there for evaluation. So uh, the compound approach is always better. Yeah, I would always go with that. The compound approach is always better, but again, uh, the situation must provide some ground for compound approach. It's not absolutely necessary that in every given situation you would be hell-bent to give a client with a compound approach. Sometimes most complex of the answers are provided both with the most simplest of the applications. So this is one of the factors too.
Okay, thank you. So next is from Mr. Fahad Imran. We have unmuted you and you can ask your question. Please.
Hello, Assalamu alaikum.
Walaikum salam.
Yes, brother, I have a question that why always we use a radiography for radiographic NDT technique for butt welds, and what is the best NDT technique for fillet welds?
Okay, Mr. Path, why butt weld is always radiograph? This is an assumption on your part. I don't think so. This is being done that frequently now. Specifically speaking, nowadays industry is moving very very far away from mandating the radiographic testing for butt weld joints. As I have 2-3 projects under my belt right now, we are applying advanced NDT techniques like phase terrain, top, and combination of different techniques for assessing the condition of the butt weld. And the fillet weld, it depends upon the specification of the weld. Usually, if the test object and its geometry permits, I would always go with ultrasonics. But majority of the situation, fillet weld is applied on a geometry where it is not permitting ultrasonic testing to be applied. So eddy current is the next best. Eddy current surface testing would be the next best.
Okay, thank you.
Okay, thank you, Mr. Adnan. The next question is from Mr. Rinju Ranjan. So we have allowed you to speak. Please unmute yourself and ask your question. Mr. Rinoj Rajan, please ask your question if you are available. Okay, Mr. Adnan, the question is on your screen. You can proceed, please.
Okay. So, Mr. Rinoj Rajan, which is the best advanced technology in RT? Nowadays, the most advanced is the computed radiographic. So, I hope this answers the question.
Okay, thank you, Mr. Adnan. So next question is from Mukhtar Mohammed. So question is on your screen. I have allowed him to speak. Mr. Mukhtar, please ask your question. Mr. Mukhtar, we have allowed you to speak. Please unmute your mic and ask your question.
Okay, I'll
Assalamu alaikum. Thank you very much for organizing this webinar for improving our knowledge. During our inspection, we have some pressure measures which is inaccessible. So which entity is the best method to do internal inspection?
Thank you, Mr. Mukhtar, for your question. I'll try to answer it as best as I can. The limitation of access is for vessel entry or otherwise? If you can
it is for the vessel entry, internal inspection for the vessel entry.
Okay. So we cannot enter the vessel, but it is available otherwise from the outside.
Yes, right.
Okay. In this situation, what I would try to do is break down a pressure vessel into its different components. For example, one of the major components would be a weld. These welds could be of different types. So one component is weld. The other is the base material, which is your shells and your top dish and bottom dish. And the other is another component would be your nozzles. So there are different NDT techniques, and they are all, fortunately, they are all ultrasonic based, which would be applicable for assessment of all these components separately. For example, if I want to assess the health of your base metal or your plate metal or your dish ends, I would rather apply ultrasonic A scanning method to ascertain if there are any areas of concern available. Or you can also apply C scanning, corrosion mapping, etc. in from the advanced fault. And for weld investigation, I would go with the top TUT or with the combination of both to ascertain the condition and health of your welds. And for the nozzles, for nozzle welds, I would go with the PAUT, and for the nozzle body, I would again go with the ultrasonic A scanning, and again for the flange faces, we would be using phase delay ultrasonic testing to ascertain the health of the flange faces. So this is how we would try to approach your limited inspection pressure vessel to health assessment.
Yeah, thank you very much. Got it. Thank you very much.
Okay, Mr. Adnan Said. That is from our
Adnan, time is 3:45 and you will be exceeding the time. I think you have to cut the question, then you can take the question at the last, because maximum you can stretch your presentation to the 30 minutes extra.
Okay, sir. So how much we have got now?
Already 3:45, you got 45 minutes now further.
Okay, sir. I'll try to finish it in time.
Maybe you can leave the question answer now, take it at the end.
Okay, sir. Okay.
Then like people who would be interested in question answer, they can stay, other people may leave. But now people are waiting for your presentation and there are many people in waiting.
Okay, sir. I'll try to finish it in time.
Thank you.
Okay, Mr. Said, please click on your presentation and please.
Okay, okay. We will continue with the presentation, and our next subject is ultrasonic testing. As I have already touched the subject, ultrasonics are a form of mechanical waves, and we use them at higher frequency ranges, and we propagate these mechanical pressure waves into our material. When these pressure waves are introduced into a given material, they tend to behave a certain way. They bounce around and they come back to our sensors, and this bouncing around and coming back is then studied as a given material and with the uniform properties is known to behave a certain way, and we know how this material usually if it's sound it behaves for against ultrasonics. So if that behavior what we get back is out of ordinary, then that behavior which is out of ordinary is evaluated for its change, and that change is interpreted as presence of any discontinuity or defect, and then it is sized accordingly. Ultrasonic testing equipment, the equipment and test wow, a very historic equipment we have posted in our presentation. Okay, so equipment used is a fundamental equipment which is called a base unit. It's a UT meter. Actually, it's a calculator and a stopwatch banged together in one system. Then we have ultrasonic transducer. If you can see this image here, this is normally termed as probe or ultrasonic transducer. Then we have a couplant, which is in between the test object and the probe. And then we have a calibration or reference or normalization block, which is this object here. This is the system we use to test different objects. Advantages of ultrasonic testing. Uh, uh, it can be almost applied to any metal or any material. If I say any material, that would not be that far off from the reality. UT works equally on high temperature surfaces, but obviously with some precautions. UT has working range in terms of thickness of material, yes, but with some certain tweaking of the package. UT can effectively and two-dimensional plan identify. Yes, RT cannot provide you with the information regarding the height of the defect, but UT can. Other techniques, the UT can be deployed to verify or to counter check performance of other NDT techniques also. Results are readily available, or I must say the results are real time actually, as the decision is being made on the spot. The equipment is very safe to operate. It has no ionizing radiation. It is battery operated, compact, very mobile, very handy to carry around. So it is very friendly to operate in field activities and very friendly to operate in remote locations. It is very portable, so you can get it inside a pressure vessel, inside a tank, and get your testing done from any location. There are also some disadvantages associated with the ultrasonic testing, which is not true that much now. No permanent records sort of thing is not true nowadays, as everything is computer aided, and we can generate almost all records, and we can retain them. Yes, the skill of the operators matters a lot. You need to have highest level of degree, if not the highest, to operate ultrasonic testing. UT is applied to material. This Yeah, with some limitations, this is true. 6.35 mm would be the cutoff limit. If you are lower than this, your ultrasonic testing normal setup would not work. But with the special setups, you can go beyond this. Uh, and frequent calibration, it's not actually a frequent calibration. It rather would be a frequent normalization of the system to remain sure that you are doing the right thing. So calibration is done once. It could be saved into the system also, but normalization you will have to do again and again. And it is not a requirement of the any specification, but it is for self guidance and self correction or self audit that you are on the right track while you are performing the day. There are also some limitations of ultrasonic testing. It is, yes, rarely used on very small thickness materials because it requires some specialized probes and equipment to get the thing done. Uh, if you are testing with conventional setup, conventional ultrasonic testing, and you are facing an composite material to test through or conduct a test of, it would be very challenging to come up with the reportable results, as ultrasonic testing is designed to operate within the realm of uniform materials, and by definition composites are not uniform. They behave differently on different layers, so it would be very difficult to come up with a useful result when you are using conventional equipment, conventional setup to test a composite material. Again, the probability of detection is very high to begin with for ultrasonic testing systems, and also it is also very important to note that the POD for ultrasonic testing methods does not go down that drastically as it is true for other non-destructive testing methods such as radiographic testing and others, as we have already gone through. And also a lot of aid and a lot of variations available for the operator to overcome these limitations and maintain a certain POD for a given situation in case of ultrasonic testing. So the versatility of ultrasonic testing system nowadays, and computer aided, and the advancement in the equipment technology nowadays has come to the aid of ultrasonic testing in terms of maintaining proper and balanced and highest POD of any given non-destructive testing method in contrast. So you can test defects of as small as 0.5 mm in conventional methods, and up to 0.01 mm if you are using computer aided time of flight diffraction testing, these sort of applications of ultrasonic testing. One more thing I would like to add, that the advancement in non-destructive testing methods is majority of that advancement has occurred in the field of ultrasonic testing. And why has that happened? Because the computers, the advent of the computer and its introduction into the ultrasonic testing realm, and the way it has revolutionized computing, record keeping, and data processing has led to the revolutionization of ultrasonic testing techniques. We have got time of flight diffraction from ultrasonic testing. We have got PAUT, or phased array ultrasonic testing, from the realm of from the world of ultrasonic testing. We have got LRUT, or alternatively known as guided waves, from the realm of ultrasonic testing. These are all ultrasonic testing, but they have got help of computers. They have got help of computer processing. They have got help of computer data retention. So they are called as advanced NDT techniques, and they have revolutionized the non-destructive testing world as of today, and is still doing so. So POD of ultrasonic testing is very high. the smallest part, the smallest defect or sensitivity is very high. The sensitivity is termed as the smallest defect that could be detected repeatedly. So the sensitivity of ultrasonic testing is very high. Obviously, it depends on the setup you have, and you can increase this also, and you can decrease this also. But as a general, compared to other contrasting NDT methods, ultrasonic testing sits on the top shelf in terms of POD and in terms of its sensitivity. So last, but in terms of I think it is the last in terms of conventional method. It is the visual inspection. Visual inspection is the use of your two eyeballs without any assistance or very little assistance to see and ascertain and to evaluate condition of any given test object. The prime example of visual inspection would be a walk around your car in the morning. You are doing a visual inspection of your car as you are trying to reach your office or your workplace, whichever may be the case, and you are doing the visual inspection of your car. If none of the tires have gone flat during the night time, if there is any sign of dripping or leakage or anything loosening up. So this is the prime example of visual inspection. We all do it. We all do it in routine. We all do it almost uh, throughout our days. But as I think most of us do not realize that we are doing visual inspection of our assets in routine. So advantages of the visual inspection is it could be done to any given thing. It could be done to a car. It could be done to a genset. It could be done to a pressure vessel. It could be done to a piping network. It could be done to a storage tank. Visual inspection can cover large areas very rapidly. Yes, you do not need to sit hours upon hours to record observations. You just give a glance. You just walk around. You just give it a shot of 2 3 minutes, 4 minutes, 5 minutes walk, and you have observed whatever could be observed from the surface, and as a result of visual inspection. It also helps you to determine the susceptibility of the location, uh, which could be the reason or which could be location of failure soon to be. Other inspection which are being performed, visual inspection can verify their application and their performance also. It is the very cost-effective inspection technique, and I think there is no cost involved in doing visual inspections. You just need your two eyeballs, and you can go around doing things. So some limitations are also there. As human beings are supposed to do visual inspections, so whatever the limitations with the human beings doing the visual inspection are, they are also part of the testing on that day. So the visual inspection can only reveal the defects on the surface you are visually seeing. It cannot tell you what is behind the wall, and you need to have a good degree of understanding of the process which you are conducting visual inspection for. Sometimes visual inspection requires some help. For example, you have a very small bore to look from, and a bore scope might come in to help you to see through that bore on the other side of that bore, to give you a visualization of what lies inside. So the limitation of visual inspection lies within the eyes. Use of the aid of the equipment, as good as your eyes are, as good as the equipment you are getting for your help, your that good your visual inspection would be. Next object is electromagnetic testing. Eddy current examination is an electromagnetic technique and can only be used on conductive materials. So inducing electromagnetic current could only be performed on the electromagnetically susceptible materials, Those materials which allow electricity to be passed through them are called electrically conductive materials, and only those materials would result in generation of produced induced magnetic lines of force. So the application of eddy current testing, it ranges from as an alternate or as a better alternate for MPI DPT to material sorting, material variation, uh, to electroplating testing, that case depth hardening, uh, uh, assessment, and also tubing inspections into the oil and gas industry for coolers and boiler tubing inspections, and for the heat exchanger tubing inspections. And these are the ranges of application for electromagnetic testing. Detection capability of eddy current belt inspection or any other eddy current inspection is material dependent, as we have already gone through. If material is not electrically conductive, you might have to make some compromises, which in turn might compromise POD. But at the end of the day, the primary question is what you are trying to find out, and if that thing you are trying to find out is being found out satisfactorily and good enough, that might be the regime for good for you. It's not absolutely necessary all the time and every time that you come up with the optimum inspection results. As I usually say to my clients, knowing something is always better than knowing nothing. So if in a compromised situation you get to know something about your asset and its condition which you otherwise don't know, it always helps in a long run. So there are some special considerations to be made before we go into doing eddy current testing of the objects. You have to have electrically conductive material. You have to have a non-ferromagnetic coating on it. If a coating is present, you have to ensure that it is non-ferromagnetic. It won't interfere into the induced magnetism in any way. Uh, some of the limitations are closed sharp edges could not be tested, as an edge would also behave like an indication itself. Local differences in the conductivity are detectable. That is how we sort materials by using eddy current testing. And the depth measurement and the depth penetration of eddy current is very limited, and it depends upon the material and the frequency of the current being induced. So eddy current testing in general application would not be very suitable to measure depths of defects or measure thicknesses of objects. In very thin objects, yes, it could do it, but in as the thickness gradually increases, this functionality decreases. Now we are moving to advanced NDT technique. I will ask for 2 minutes to have a glass of water as my throat has dried up. Sorry, everybody. Let's get back to the business. So, in terms of advanced NDT techniques, we have got quite a few for your introduction today. Some of the advanced techniques are listed here. Real-time radiography, because it has managed to get some help from advent of computer and computation power, data processing power. Automated and semi-automatic ultrasonic testing, time of flight diffraction, C scanning, guided waves. As I have already gone through majority of the examples written here, and that these are advancement in ultrasonic testing because based on availability of power of the computer to calculate and to maintain and process huge amounts of data being gathered from ultrasonic systems. I think there's some discrepancy into our slideshow. nonetheless, we'll move forward. Real-time X-ray radiography. In real-time radiography, no film is used, and the result is directly displayed on the viewer or on the display screen directly with a very improved quality compared to radiographic film. This is an X-ray based system, so it only emits when it is being energized. In this special case, in case of RTR, the radiation is not supposed to penetrate through the pipe wall thickness. Therefore, we get a profile of the pipe surface on the screen. What are the advantages of RTR? Main advantage is the safety aspect, as no unnecessary exposure to ionizing radiation is there. So it is safe to operate without associated radiation hazard. Automated and semi-automated ultrasonic systems. One of the prime example are use of ultrasonic crawlers to measure wall thicknesses on high-rising components such as columns and storage tanks. These systems use softwares and computers and crawlers such as these and different type of scanner to make an ultrasonic sensor which is just about mounted here, and the principal working is same. The sensor is mounted here. It is connected to the preamplifier. The signal is sent back to the control module with the help of this cable. It's around 60 meters cable. It goes to the ground where the operator is sitting. It has a control module which processes the data, sends it to the computer, and then computer manipulates the data and presents its operator with the readable form. So the fundamental function is pretty similar, but the only introduction of this automated scanner has improved the functionality or the utility, because an operator without the help of scaffolding cannot go and measure ultrasonic thickness of an object 13 or 14 meters above ground. So these are the systems, automated systems, which we use to get ourselves the amount or the type of help required to get those type of tasks done. What are some of the advantages of using semi-automated and automated ultrasonic system? The main advantage, as again I would repeat, is the use of computational power of computers, data processing power of the computers, and maintenance of the digital record of the inspection which we have carried out. This is the first and the foremost, by far, the most beneficial advantage of automated systems in non-destructive testing. In some cases, when your assets are at elevated temperatures, human beings cannot interact with those assets or cannot come closer to those assets. Some specialized scanners are utilized, which are automated in their nature of operation, and instead of a human being, those scanners go to the asset and they conduct inspection on behalf of a human being without getting damaged, as they are specifically designed for those extreme environments. AUT is also very rapid in its scanning speed. It also provides with additional details as the computational power of computer is available. You can manipulate data and extract additional aspects and additional information to use other advantageous environments. It's extremely accurate and it is actually extremely repeatable. You can go and repeat your test again and again on a given situation, and also use computer's power to keep track and monitor the record of propagation of any given defect for a certain period of time, for a year, for 16 months or so, to establish what the growth rate of a given damage mechanism. Either it could be a corrosion, or it could be an erosion, or it could be a crack which is propagating. You can maintain the log of that propagation for prediction of future usability. Some of the limitations are also associated with, as it is for most of the NDT methods. It has some multitasking features, complex scanners, complex computer systems, complex multiple parts are involved, so it gets complex for the operator to handle sometimes, and can lead to human errors. This is the foremost limitation of automated UT. Next is the time of flight deflection. Time of flight deflection is a pitch and catch method, in which we flood the part with ultrasonic energy, and if there are any defects which are present into that material, they would start behaving like ultrasonic sound emitting sources themselves. And then those emitted sounds, or those vibrations which are generated by the defect itself, are detected from the receiver's end. And time of flight deflection is not orientation dependent like other NDT methods, as it does not rely on reflected signal. Rather, it depends upon the detection of diffracted signals. So it is independent of the defect orientation. So it is very reliable and very accurate in its defect sizing and positioning. So it is also an advantage of time of flight deflection against some of the other NDT methods, specifically speaking, other UT methods, such as pulse echo or PAUT. They rely on the detection of the reflected energy, but TOF does not rely on the detection of reflected energy. It relies on the detection of diffracted energy. So it is very accurate in sizing. It is very accurate in predicting the position of the defects. It has the highest probability of detection in any ultrasonic based testing method. So it is very efficient. In again, if you pitch it against the X-rays or gamma rays for weld investigation, it far exceeds the effectiveness of X-ray systems in terms of detection and sizing. There are some disadvantages associated with the Toft also. Um, it only works with the very fine grained materials, as it is a very high frequency application. So if you have a coarse grained material, the background noise generated by the grain boundaries would render the results unreadable. So you have to have some very fine grained materials in the first place to test them with time of flight deflection. As per some specifications, Toft is limited from not to be applied on thickness ranges below 6 mm. And as per some specifications, the thickness is 13.5 mm, which allows application of Toft. Toft has the highest accuracy in wall sizing and crack sizing, and it has the highest POD in any given NDT method. Next is our creeping head wave inspection method, or large area scanning method. This is also a pitch and catch method. This is used to screen large objects for presence of any wall losses or other associated damages. Specifically, as you can see in the example, this is especially applicable on the areas which are hard to reach or unreachable by the techniques otherwise, such as direct contact methods. The prime example is the area directly underneath a saddle support of a pressure vessel or LPG bullet, which remains untested by any other method, which requires direct contact to the test surface. By applying chime, you can assess the condition of the object under saddle support, and then you can specifically locate that any area of interest if you manage to find it, and then you can plan your off streaming of the pressure vessel and address that specific area for the presence of any defect or any serious threat to the integrity of the asset that way. So how does it work? At a given instance, uh, uh, shear wave and head waves are introduced into the material bulk as a bulk wave. Uh, they follow the critical angle along the walls, interior and exterior walls of the of the material, and on the receiver's end, when they are received, the lost energy is calculated, which is constant for a sound material, and if that lost energy is above that constant, it is perceived to be presence of any feature that has caused that additional loss, and the amount of loss of energy is then converted into the percentage of fall loss or percentage of cross section that has been changed in that given circumstance. Then we have got the long range ultrasonic testing, or alternatively known as guided wave testing. It is again ultrasonic based testing. It uses lamp waves or plate waves. Again, help of the computer is available, so we can utilize hundreds of sensors at one given time. We mount our ultrasonic ring, which has these modules. Each module carries multiple sensors tasked with different target. So we mount this ring onto the given pipe. Every diameter of the pipe has its own specific ring size, and then ultrasonic is transmitted into the pipe structure along its axis, and then the features into the pipe structure, like weld joints, presence of corrosions, flange joints, supports. These features generate their own reflection onto the time trace, and those time traces are then interpreted as into the results and marked as areas of concern. Like these are areas of concern, then these are evaluated in terms of actual thickness remaining and reported to the client. So this can scan long lengths of pipes up to 30 meter on both sides from a single point. This is true on majority of the cases, but this has to be taken with a grain of salt, because each application has its own sets of limitation. And when someone asks me what is the typical range of LRUT, uh, I would refrain from giving an absolute number. Yes, it provides long ranges in certain situations, but until you get first data set from a given situation, you cannot put a number to that, and that first test always provides you with the behavior of the structure on that given day, on that given test. It works with very low frequency ultrasound, normally in the ranges of tens of kilohertz. So it has a very high penetration power, and so that helps it to attain very long range testing regimes. Personally, I have tested almost half a kilometer in single shot with guided waves system, but that is not uniformly equal for any given situation. Equipment is now available commercially, but is very costly. So developing and maintaining the capability of getting LRUT done for anyone, it has a significant cost impact. Also, you have to have a financial capital, and you have to have a resource in terms of very capable, highly skilled resource capital also to maintain and operate that system. Otherwise, you're gonna lose it in couple of jobs. Okay, as sensitive as 3% of the cross section change is detected by by the system, and usually the reporting threshold is set to be at 9%, and above 9% changes are reported to the client, and usually 23% and plus cross sectional changes are uh, uh, followed up with a complementary technique to calculate and to establish what is the remaining thickness on that specific location. Um, Advantages of LRUT are it's rapid, it's very fast in terms of screening. It provides you with the areas of concern with high efficiency. Uh, you can run through kilometers upon kilometers of pipe work in a single day, and then you can target specific regions based on the results of your LRUT for accurate remaining life assessments. It cannot detect an isolated pit. Yes, it is designed to detect some area of concern, and area by definition means there has to be some length, width, and height for it to be detected by LRUT. For cost effective and for time effective, a minimum length of 5 meters is required. Uh, it can be tested up to the tubing thickness and tubing diameters, and 100% of the circumference of the pipework is screened for wall loss. So the next is our phased array. Let me put one thing into your perspective as we begin with phased arrays. Phased array is no more than conventional entity, conventional UT testing, but uh, in conventional UT setup, we have got one instrument with one probe having one element at a fixed angle, and you have to deal with it. But when you come to the phased arrays world, you can have up to you will have to handle up to uh, hundreds of systems in terms of availability. Depends upon your probe you are using and the setup, but you can have hundreds of elements at one given time, generating hundreds of different angles at one given time, and generating a combined image of all those testing parameters for your given application. So handling hundreds of probes at a given time required so much computation power and so much data processing power that it was impossible to do without help of uh, computer processing power available nowadays. And as soon as we have got computers in our hands, ultrasonic testing started to revolutionize, first in the form of phased arrays, and now in the form of TFM and full met FMC and TFM sort of applications. So the fundamental principle is same as it is for conventional shear wave testing or longitudinal wave testing, straight beam testing, but that is operating with one element at a time. This system is now operating with hundreds of elements at a given time. It has no safety hazard as it is operating ultrasonics. Uh, you can proceed with the inspection as soon as the weld is cool. It has a better defect detection and sizing capability as it is operating with so many different angles at a given time. If one angle is missing something, the other would see it. Has great flexibility in parameter range. Yes, you can make your system generate whatever parameters you want Obviously, those have to be within the realm of practical possibility. PUT is compliant with all known codes and standards. Yes, it is compliant with absolutely all codes and standards as of today. It is some of the disadvantages. It is not preferred to be used for crack sizing, metal fatigue, and bolt hole and tubing inspections, as the application limitation is there. The angle of incidence is not always optimal when using S-scan. Yes, you have to make a best possible compromise without affecting quality. Yeah, the training of the professional which uses these systems is required to be of the, what would I say, out of this world. It has to be extensive training. You have to have a very good understanding of fundamental physics in the first place. You have to have some understanding of electronics in the second place, and you have to be on top of the mathematics. So it is some work to be done. Uh, it is a very costly equipment. Yes, it to maintain and to operate it, it involves a lots of capital. So this is one of them. Obviously, when you invest in such a costly setup, you charge it back to your client, and this is the cost of testing. The next is our eddy current testing. Eddy current test surface testing, as we have gone through, is the same phenomenon, but this time the probe is shaped into the form of a bobbin coil, which is inserted into a tube-like object for assessment of health of the boiler tubes, heat exchanger tubes, and other tubing structures. It's used for the heat exchanger tubing inspection, periodic testing of elbows of the boilers, uh, for the damage mechanisms which could lead to failure. There are some limitations of eddy current tubing inspection. Uh, it it does not do well with the non-magnetic materials or electrically non-conductive materials. So you have to have ferromagnetically electrically conductive materials. However, some uh, some new techniques such as IRIS, which is ultrasonic based, or NFT, which is near field testing, or eddy current biased testing. These are some of the newer techniques which could be applied to overcome these limitations for specific applications. The far field eddy current testing, one of the prime example of overcoming those limitations. So the latest into the world of eddy current testing is pulsed eddy current. So we first had pulsed phased phased arrays or in ultrasonic testing, where we had multiple elements doing different things at the same time, and then combining all those different results into one big picture by the power of computer. Then we have got same thing going for eddy current testing. Earlier we had single equipment with single probe doing single thing at a given time at a single time. Now we have an array of probes with multiple elements or coils inside it doing multiple things at a given time, and then we combine all those testing parameters into one big picture to give our clients and our users a bigger picture of the damage mechanism, if applicable to their asset. It is very easy to use. Equipment is very portable. It takes less than 5 seconds to give a measurement. It can measure wall thickness through insulation and coating up to 120 millimeter thick. It can measure wall thicknesses from 3 mm to 30 mm. Obviously, above 30 mm, the penetration limitation kicks in. Uh, It is not very sensitive to very localized defects. However, for large area damages such as corrosion under insulation, which usually affects a large area of any given asset, this can map the damage and give you results so that you can plan your maintenance run. Similar to eddy current testing, it has a probe coil. It has a magnetic field induced into the ferromagnetic material. Then there are eddy currents generated into the ferromagnetic material, which in turn generate their own magnetic field, which resists the induced magnetic field, producing a balance between the net magnetic field, which is called capacitive reactance. That balance for a given sound material is constant. And if that balance is disturbed by the presence of any defect, this imbalance is then calculated into evaluated and interpreted into the presence of defect and then used to size it. Pulse eddy current inspection advantages are its larger penetration depth through the insulation material. You do not need to remove the insulation to ascertain if there is any presence of CUI or not. It can do that for you without removal of insulation. As we have gone through already, the wall thickness limitation is between 3 to 30 mm. Standoff you need is 120 mm. Cladding must be less than 7 mm in thickness. It cannot be performed on difficult geometries because you need references to move along. Cannot specify if internal external wall loss. It only monitors the wall loss. If it cannot differentiate if the wall loss is internal or external. It can detect small but deep defects. It cannot detect the isolated pitting. It is not suitable also for the areas which are exposed to excessive vibrations. Alternating field measurement technique it's also an electromagnetic technique, which is a non-contact method. So the principally the in uniform electrical current is induced into the product, and then a resultant magnetic field is produced. This technique has some advantages associated to it. It is sizing technique based on mathematical modeling of the surface magnetic field. It is able to determine defect depth without calibration. The technique is also capable of inspecting through coating up to 6 mm thick, under normal conditions up to 12 mm thick if required, obviously with special tools and tackles and special setups. Currently, it can only work on steel. The length assessment is not very accurate when sizing cracks. It is still model based, so a chart based recognized that defect is used. After that, it can be used to translate ACFM indication depth into true depth. A model is generated. It is not actual. It is modeled. So it could be off by quite some margin. Its performance models or sizing models perform well on the cracks, but other damping mechanism could not be sized that effectively. Then we have IR thermography, infrared thermal imaging. This techniques detects any thermal gradients being radiated from a source of heat or being artificially heated objects. In IR testing, we usually see thermal gradients coming out of heated objects in the form of infrared spectrum emission. So we have specialized cameras and specialized filters designed for that, which detect IR emissions, and based on the intensity of the emissions, we can calculate and we can measure the actual temperature of the test object, and then use that information to come up with the planned maintenance of that object. To better come up with the accurate results of thermography, we need to have some basic and fundamental understanding of some of the elements involved, method of heating, size of the defect which we are trying to find, uh, the rate of heating and cooling which is involved, synchronization of thermal pulse and image acquisition, thickness of the coating which could damp the IR emission, optical reflectivity of the coating. Advantages. The main advantage of infrared thermography over destructive testing method is that uh, it can rapidly scan vast areas for any potential point source of IR emission, and then that specific point could be targeted for the mitigative action. The instrument is very risk-free. It does not emit any radiation of its own. It is very portable. You can take it anywhere. There are some operation or environmental operability limitations associated from the manufacturer, and that is usually within the limits of what we usually see in our industries. So it is almost applicable in any environment, since any every other NDT method so far had some limitations. So thermography is not uh, uh, exempted from that. It employs infrared equipment. It cannot penetrate the great depths, only a few millimeters, because infrared radiation does not penetrate very much. Part of the light spectrum is very weak. Finally, when you are conducting outdoor infrared thermographic surveys, the environment uh, plays an important part, because everything is radiating IR. So you can have influence from all sources of IR emission in your environment, and you have to be very careful what you are reporting when you are doing IR thermography. Last but not the least, I think, is the acoustic emission. Again, acoustic emission is a passive NDT technique. It utilizes the uh, some of whenever acid is in operation, it is under stress, and when those stresses are generating any defects or causing any deformation or damage in that acid, it emits certain stress waves, and those stress waves are then detected by specialized sensors mounted on different locations of the acid. Then the collected data is transformed into human audible ultrasonic ultrasonic spectrum, and then triangulated for location. It is then evaluated and interpreted for the type of the indication, the location of the indication, and the severity of the indication. And it is purely screening technique, and it does not provide you with absolute numbers. It is qualitative, not quantitative. It offers more conventional ND techniques, is that it results directly from the process of flaw growth. If a flaw is present and it is growing with the stress being introduced, it provides you uh, with the alarm. It has some limitations associated. Some of the normally occurring phenomena, such as scaling and deposits, they also generate AE signature, which oftentimes confuses the interpreter or operator when he is evaluating the result. Sometimes it becomes impossible to distinguish between actual damage and false indication. So these are some of the limitations associated with acoustic emission testing. Thank you everybody for your time today. I hope you have enjoyed our interactive session.
Okay, due to lack of time, we will only entertaining around 3 questions, maybe, or 4. So let's start with Mr. Kashtif Mushtaq. Mr. Kashtif, are you still there? Can you please ask your question? Unmute your mic, please. Mr. Kashtif Mushtaq.
Can you hear me now?
Yes.
Yes, I can hear you.
All right, that's great. First of all, thank you very much for this, very informative webinar, and did provide us an opportunity to, have more visibility on the constellation of different NDT, conventional and advanced test itself. So as it's written over there in the question and answer text box, I need to understand that how do you plan yourself for the mix of the test that is required for a specific asset, and how do you start that one? What are the kind of a checklist that you go through it, and then afterwards you decide that okay, these are the conventional test, and these are the unconventional test or advanced test we need to conduct on it in order to reach to some recommendations, and or before recommendations, the observation itself. So if you can shed some highlight on this one, and how do you relate all these kind of results or recommendations with respect to adding into the sustainability goal of the client? How does it impact on the energy efficiency and the carbon footprint reduction of an asset? Thank you.
Adnan, I can answer this question in a better way. First of all, the energy efficiency and carbon footprint is out of context of this discussion, so we'll not be touching that because they're different concept. However, I can explain. I'm audible, Adnan?
Yeah, I can hear you.
Okay, okay. So let's take an example of a heat exchanger where we need to develop an inspection plan. The basic guideline, which will be coming from API 510 and then API 572, the basic inspection needs would be there. Then there would be applicable damage mechanisms. So, and then if there's a crack or localized metal loss or generalized metal loss or insulation. So keeping those considerations in mind, the technique would be like UT gauging, UT scanning, and if there is any kind of crack, subsurface crack we are expecting, then advanced entity like TOFT or TOFT or phase array would be coming into picture. For heat exchanger tubes, since normal conventional NDT cannot work, so we have to think either IRIS or eddy current. IRIS is for carbon steel tubes, and eddy current is for basically non-carbon steel or SS tubes. So in this way, we are making the combination first visual inspection, then UT gauging on the spots, UT scanning on the weld seams, and TOFT or PAUT on the areas where we are expecting some subsurface cracks. Then on the tube side, there would be, like as I said, IRIS or eddy current. In this way, the combination of conventional and NDT techniques is formed. If you want to add further, Adnan, you can add if I miss something.
Sir, you have done a marvelous job.
Thank you very much.
Thank you, sir. Next question.
Okay, next question from Mr. Ronnie Isaac. You're already unmuted. Please ask your question, sir.
Yeah, good evening. Actually, I was raised a question to check that what is the success rate of detecting the remaining thickness under a pitting using density comparison method.
What is the success rate of using profile radiography to detect the remaining thickness of a localized pitting using the density comparison method?
Here again, Adnan, I can answer that. See, first of all, the profile radiography is used for small bore pipes up to 3 inch, right? Profile radiography cannot be used for bigger dia pipes or straight pipes like diameter or plate, where you cannot use angular position of the camera. So the profile radiography is used for small bore where the micro probe of UT is a problematic or it may not fit on the outer surface of the pipe. So the accuracy rate of the profile radiography is better as compared to UT for the small bore pipes. That's my understanding. And Adnan, you can add further if I miss something.
As far as the detection is concerned, if you are using profile radiography in screening mode, obviously that is what it is designed for. It has to be on the spot every time. The success rate question would go out of the window. But I would like to know what is the profile radiography for this specific question is being pitched against. If it is being pitched against ultrasonic testing, then yeah, profile radiography would sit on the top shelf every time. But if it is being pitched against some other screening technique, then we have to come up with some number that profile radiography is performing. Even then, if in the screening mode and you know the area of concern, it has to be on the spot every time. So I think Ijaz sir has already answered the question, and I have added whatever the confusion remains.
Okay, go next question, please.
So just can we go for the last question now?
Yes.
Okay.
I'll be late. Yeah.
For last question, Mr. Jason Kalur, can you please unmute your mic and ask your question, please? Mr. Jason Kalur. Okay, he's not unmuting. I will just read his question for you, Mr. Adnan. Calibration or sensitivity checks done prior to testing an area of interest in NPI or PT method to confirm the method works. IQS. It's in the screen.
So it's not IQI. If I have understood your question rightly, in MPI when we do the prior check of we do a check for orientation of the defect and the component which we use is called Castrol shims. It tells us the sensitivity of the overall system, the smallest the defect we can detect, and then we use a pi gauge which gives us some idea of what the system is generating in terms of orientation of the induced magnetism, so that we are aligned in perpendicular of the predicted path of the defect, so that we give our system a chance to come perpendicular or interact on the major axis of that defect, so that we have a better probability of detection. I hope I have answered your question.
Okay, thank you.
Okay, Mr. Adnan, thank you very much for having this very informative webinar. It was very flow was very I would say in a proper order, and I am impressed by your presentation. Keep it up, your effort for future. And for audience, thank you very much for your day, and we look forward to your attendance for the next webinar. Thank you very much, and have a nice
Thank you very much, everybody. Thank you for enduring so long.